You have order 10 to the 52.
Yeah.
Then I would argue that even the early time radio observations rule that out.
If it's
Because the noise factor of a few, it doesn't take, it decelerates. What's it decelerating?
Depends on N also.
Yeah, but it's not very,
It's
very
low N, energy, okay, it depends on E over N, and then sometimes gamma.
Yeah, but I'm just saying that I definitely agree that if you had only a mildly relativistic outflow, it could take a few weeks.
Right.
And so all of our early observations are just too soon.
we're gamma, yeah,
If
gamma
it's
1.5.
gamma of a few, or 5 or 10, as you're saying, then it should decelerate reasonably quickly.
So I guess the question is how high of gamma we think that this thing may plateau. I guess that's one question. You could take the extra energy in the plateau and say, okay, if that were put into gamma greater than 2 or 3 stuff, what would that do for the early observation? I guess. For whatever densities you and epsilon you infer.
Yeah, because we have a lot of limits. As I showed, 90% of our observations are limits, and I wonder if the already place an interesting constraint.
But again, I think
For the
the range
spitwise,
issue, we don't.
you know,
Yeah, there's still
there's
a
a
concern
little
that
bit
we
of
understand these. You know, I mean,
Yeah.
there are radio signals which you infer quite low values. So it's not clear if there's something different going on in relativistic shock.
For relative, because they actually for GRDs, some of them they derive absolute, like Thomas Mark has several papers regarding
Well,
these GRDs.
but that's a very different.
No, you can generally you put some so say UC has to be
Larger. I mean, the reason he's getting this very low epsilon B's is he's saying I have to have the frequency very high.
yes, yes.
To explain the GUV emission.
Or
Again, there are other
in
models.
the case, UC goes up to
Yeah, I have a colleague at Columbia who's very opinionated about
Which ones?
Well, Bill Brodov, he has his own.
No, but which models?
Oh, the ones where the
Ones?
forward shocks, yeah, the GAV.
Yeah. Then that would relax. That would remove that need for epsilon B of 10 to the minus 7. That Pollen is getting. He was getting very low.
But his
These
GV,
pairs.
yeah, I think that's earlier.
Okay, the later.
It's
Still need a low.
I don't want to.
He's not there, so you can't sit there.
The problem is that it can't be the case always, because we do have cases where we know that the core frequency is below the x-axis. So maybe the lot sample is different.
I don't even know what you're looking.
Yeah, I don't look, but if epsilon B is very low.
Well, they may have probably.
Yeah, but let's say that for that component epsilon B is low, then you wouldn't see the early time and you wouldn't see the late time. Right, because.
Well, that's easier than
Alright, I'll be right there.
Is that what you look at almost?
Well, you do, because I saw the notes you just sent.
That's right, yeah.
Continue innocent. And you're not innocent either.
Yeah, no.
That's not,
But,
I know, it's almost here.
yeah, it's our process. It's very different.
Just wait till you read the note. There's no modes in there. It's all back of the envelope.
Oh, yeah, I know, I saw that.
There's no eigenfunction.
I saw that. And you weren't even rude about our paper.
My eigenfunction is the top hat.
Do I need to bring a child seat in the car if I'm bringing you a letter? All right, shall we get started and let people trickle in if you want to? Okay, so it's
Okay.
Yuichiro here. So
Yeah. Thank you for giving me a chance to talk.
I'll put it right, but
It's fine. Just make sure
Oh,
that
it's
this is all good.
Okay.
cool, very good. Go ahead.
Okay. Okay. Thank you for giving me a chance to talk on our recent paper, this paper. And my name is Yuichiro Sekiguchi from YTP, and here's my collaborators. Okay. So the top title of my talk is Binary Neutron Merger and the art process. And as you know, the neutron capture processes can be divided into two: wide rapid neutron capture process or R process, and the other is S process. In R processes, the time scale for the neutron capture is much faster than the beta decay. So in these R processes, the neutron is basically freely packed into the seed nuclei, and makes very heavy neutron-rich nuclei. On the other hand, in the slow neutron capture processes, the time scale of the neutron capture is much longer than the beta decay. So in these S processes, the nuclei evolved along the stable valley line. And this R process is a topic of my talk. And this is the chart of the nuclide, which shows the path of the S process in this magenta and the R process in blue line. And the horizontal and vertical axis denote the neutron number and the proton numbers. And if you take this axis, this is actually the axis of the mass number A. You can see along the R process, you can see that several peaks, actually 3 peaks. And now I'm concentrating on this gold. Gold is in third peak. Okay. So here I'll show you a recipe to make a gold, according to which you could be an alchemist. Basically, neutron capture process is the packing of neutrons into a seed nuclei. So if you want to have big nuclei, you need this ratio, large number of neutron to number of seed ratio. And if you want to make a gold, this ratio should be 100. So if you want to have such a large number of neutron to number seed ratio, you need a large number of neutrons, so you need low electron fraction, Ye. Also, to reduce the number of seed nuclei, the higher entropy per baryon and the short expansion time scale is helpful to reduce the seed nuclei production. So roughly speaking, we need some explosive. Explosive means the short expansion time scale and the high entropy per baryon with low electron fraction to make R process elements. And the astrophysical site of this R process is still under debate. But there are 2 candidates for the R process site. One is supernova explosion, and the other is the compact binary merger. And sorry?
Back to the previous slide, you say observationally disfavored?
I'll explain later.
You'll come to that? Okay.
Yeah.
No, I'm just wondering.
Yeah.
So I'm just wondering what's the argument?
The supernova explosion have been previously considered to be a promising site of the R process, but now likely to be theoretically disfavored. This is because the recent progress on the supernova simulation have clarified that the entropy per baryon achieved in the explosion, the real or numerical supernova explosion is somewhat lower than the previously expected. So this gives you this contradicts from this condition, and the number of seed nuclei is becomes increased than what was expected previously. Also, more seriously, the neutrinos from proton-neutron star makes a flow proton-rich according to this reaction. This is inevitable because if you adapt the standard neutron heating mechanism as the supernova explosion mechanism, this neutrino heating is inevitable. And according to the latest simulation, only weak R processes. This means that up to second peak in this chart is produced in this supernovae. No gold, no third peak. This figure shows the how much how the the dependence on the peaks obtained peaks in terms of neutrino temperature and anti-electron neutron temperature. To make a third peak, we need huge difference between neutrino temperature and anti-neutron temperature. Otherwise, we cannot overcome the mass difference between neutron and protons. Basically speaking, because mass of the neutron is larger than mass of proton, the nature goes this way. So to overcome this nature tendency, we need some big difference in the neutron and anti-neutron electron temperature. But according to this latest result, with changing the nuclear parameters and the neutron parameters, the difference what we can get is at most 5 MeV. And this 5 MeV is not sufficient to make a third peak. This is the problem in supernovae explosion scenario. And if the supernovae explosion can be origin of our process only if so the explosion is not due to the neutron heating. For example, magnetorotational, or our knowledge of neutrino and nuclear physics is insufficient. Okay, let's move on to the computer.
What's wrong? So what's wrong with the magnetorotational?
This scenario is okay, works well, but this assumes that all of the supernovae explosion due to magnetorotational.
I don't think that's necessarily true. I mean, the ejected amounts in these are much higher than from the neutrino wind.
Yes.
So you could actually get away with a fraction of the
Yes,
supernova.
yes. So depending on the amount of the mass per event and event rate, so it's not clear. But if you agree with this scenario, it is possible to make all of the process elements by this
When you
magnetorotation.
say the theoretical disfavored, then there must be something wrong with this.
Yes, theoretically disfavored if you adapt the standard neutron heating mechanism.
Yeah, I mean, what you're assuming there is that the ejecta is neutrino-driven wind. I mean, you can get, the ejecta is driven some other way, you may not reset the YE.
Yes. So we must get rid of this interaction. Otherwise, the flow becomes proton rich.
But there's also even if the YE is set by that, the magnetorotational can reduce the expansion time.
Yes.
So even if the YE is reset, this helps push you towards
Yes.
but maybe not enough.
Yeah. In this case, because the explosion time scale is much shorter than this standard neutron heating mechanism, then we can avoid this problem. And previously, compact star merger scenario was observationally disfavored. Previously, from the chemical evolution viewpoint, this figure compares the observed abundance of the European as a function of metallicity. This H is basically metallicity, and the increasing direction of the metallicity is the time is chemical age. And the left figure is for supernovae model, and the right figure is for binary merger models. And the red point denote the observation, and the black dot denote the model prediction by the Monte Carlo simulation. And let us concentrate on the binary merger model. And the simple model based on simple mixing and a very simplified model predict first delayed appearance of the outpost element, because it takes time to the merger and to expel the outpost element.
So what's being assumed for the delay time distribution?
Sorry?
What's being assumed for the delay time distribution in this model?
This model is 10 to 8 year,
As a minimum?
typical. And there's some distribution.
I don't understand this very significant delay because
So if you are, at that time, there is only model. And recently, Bertinsky proposed there is some population in which merge is much earlier, much shorter time scale. But at that time, they adopt a longer merger time.
yeah, I'm just surprised that a delay of 10 to the 8 years gives you such a significant delay.
Yes.
It's not only 10 to the 8, it's 10 to the 8. They assume 10 to the 8 minimal delay,
Yeah.
10 to the 8 years, and then a distribution of delays.
Yeah.
So most of the event takes much
Yeah.
longer.
Yeah.
It's this without going into the detailed assumption of this model, it's not worth showing this figure. Because this figure, the model, there are several assumptions here. There are numerous assumptions here. Without these assumptions, you don't know what it is meaning, what the meaning of this figure.
Mm.
Yeah.
All that you know is that somebody made some assumption
Yes, yes.
and got some model. That's all that you know.
Yeah.
Without going into the detailed assumptions here, this figure is meaningless.
Yeah.
Yes, yes.
And in support of that, Enrico Ramirez-Ruiz was saying maybe you're going to show it, but he seemed to be arguing to me that, in fact, he needed some delay to explain the observations, which I would like to see how is he getting something different than our guys. And I think it is the assumptions that they're making.
It's just
Also, you can see the large scattering in this region. This is basically due to the
wrong model of mixing in this model.
yeah, in this model, the mixing is the same as supernovae. But this is a problem because the expansion
This is the wrong mixing models.
is same mixing model, same mixing model.
They assume that the mixing is only within the
Yes,
nearby
yes, but the okay.
50
As I said, as I will explain later, because the expansion velocity of supernovae and the binary neutron star merger ejector is completely different. So this same adapting same mixing model is not good. But in this paper, they adapt the minimum merger time of 10 to 8 year and the same mixing model between supernovae and binary neutron model. Then they obtain such a figure. And they claim that you can see the delayed enrichment and the large scattering. So they conclude that the binary merger model is disfavored in some observational sense. But as TV pointed out, if you change the assumption, you can change this figure. Recently, Tsujimoto-san and Shigeyama-san do such a job. Their result is based on the observation of the dwarf galaxies. First, they find no enrichment of europium. Europium is a typical and representative out-process element, so that no enrichment of europium means that there are no out-process event in some ultra dwarf galaxies. But they do observe the enrichment in iron. This means that no out-process events, but there are supernovae events because of the enrichment of iron. If the supernovae is the origin of our process, such assumption contradicts this result. Okay? On the other hand, they do find enrichment of europium in some more massive dwarfs. And the event from this result, they estimate the event rate, and which is of order of 1,000th of the supernovae, and which is consistent with the binary neutron merger. Also, they take into account the difference of the velocities. Because in the binary neutron star merger case, the ejector have much higher velocities, 1,000 times faster than the usual supernovae. And this means as a zeroth order, ejector spreads 1,000 times farther than the usual supernovae. If you take into account this fact and making some mixing model based on this difference, you can resolve this larger scattering in the later phase.
Did you understand their model for why the ejecta flies 1,000 times further? As I was reading it, it's something about
This is based on the numerical.
ionization losses, but
This is based on the numerical relativity simulation.
Sorry, it's from
This is based on the numerical relativity simulation.
a numerical
Relativity
simulation of
yeah.
the ejecta interacting
Yes.
with gas?
Yes.
Okay, that's what I
Yeah,
remember
yeah.
from their paper. So you're going to show the simulation?
Yeah, I'll show you
Okay,
later.
okay.
Yeah.
Because I don't think that was in this
Yeah,
paper.
yeah, yeah. So now this figure shows the no enrich. This figure shows the no enrichment in the European. Oh, no, okay, so no enrichment in R plus elements in the ultra-faint dwarfs, and this figure shows this enrichment of R plus elements in some massive, more massive dwarfs. Okay. And as a further evidences, as Ed already talked, electromagnetic transient, possibly powered by radioactive decay of the R plus elements, which was first discussed by Lee and Paczynski in 1998, is recently detected, accompanied by the supernovae. Supernovae 130603b. So this is also supporting evidences that our compact binary merger is the origin of the R process. Here. Here, let me remind you an important observational issues which should be seriously taken into account in considering the origin of R process elements. This figure shows the observation of the isotope from the mass number of 30 to 90, and the result is for the very metal clusters. And this point is observation, and this blue curves solar abundance pattern. And the very metal poor means that these stars are influenced by only one or two R process events. Okay? Nevertheless, these abundances in these stars shows remarkable agreement with observed solar abundance pattern. This means that this solar abundance pattern is not a result of some mixture of some diverse abundance pattern, but in each R plus event, the system should produce a heavier element fairly consistent with this solar abundance pattern. This is so-called the universality of the R process side. So if you consider the origin of R process, this universality is one of the smoking gun. Every model should produce approximately this solar abundance pattern. And to this regard, the compact binary merger was not good in terms of this universality. This is first discussed by the Korobkin et al. In 2012. They claim that the electron fraction of ejector is very low according to their Newcomen simulation, like say less than 0.1, and depends only very weakly on the binary parameter. So that the R process in the neutrons and neutrons is robust, making a very low electron fraction. This is a result by Korobkin et al. And this is a fraction of the mass in terms of the electron fraction. As you can see, the electron fraction is basically less than 0.1. And if you have such a low electron fraction, it is impossible to make this first peak. Only third peak and second peak can be reproduced. But this, the lack of this first peak is contradict with this universality. Okay, but this result is drawn by very limited simulation because they adapt only one stiff equation state. So dependence on equation state is not explored. Also, they adapt Newton SPH simulation and the GR effect is not included. Okay, before going further, let me remind you that for the mass ejection from dynamical mass ejection from the merger, there are two components. One is a component which is ejected due to the tidal effect, which basically goes along the orbital plane. And this matter consists of cold neutron star matter in beta equilibrium. This means that this material have low electron fraction and low temperature. On the other hand, we have another component. This component is almost isotropic, and this means that this component is driven by shocks. And this matter consists of hot shock heated matter, and the temperature is higher, much higher than this tidal component. So being temperature high, weak interaction can change electron fraction. So please remember that there are two components. One is driven by tidal and with low electron fraction temperature. The other is driven by shock and the temperature is higher, and the weak interaction can change electron fraction in this component.
Sorry, what is color coded there?
This is density, density. Gram per cubic centimeter. And the true nature of the ejector property must be a mixture of these two. And we need numerical summation to obtain it. So in this talk, let us consider first the dependence on the equation state and compare the result between two equation states. One is SH, the so-called FHO equation state, and the other is Shen EOS. This figure is the relationship between mass of neutron star and the radius of neutron star. And this SHO neutron star gives you very compact, small radius neutron star. And on the other hand, Shen EOS gives you larger radius neutron star. And in terms of current understanding of the current modeling of the neutron star matter, these two are basically most compact one and most less compact one. And as I explained, for Shen EOS, which is stiffer, because the radius of neutrons are larger, it is expected that mass ejection is mainly due to the tidal forces. On the other hand, for the compact SFHO EOS, because the radius of neutrons is smaller, tidal effects are less important, and the mass ejection will be driven by shock heating. Before proceeding further, let me remind you again the importance of electron fraction in the R process in the binary merger. This figure illustrates how the R process yields depends on the electron fraction. Okay, so this red line shows the result for the electron fraction of 0.25, and this red dotted dashed line is for 0.22. So roughly speaking, electron fraction of 0.2 is critical threshold. For the electron fraction less than 0.2, the result is second and third peak is produced, this means that the strong R process proceeds. On the other hand, for the electron fraction larger than 0.2, we cannot make this third peak. This means that only weak R process proceeds. And as I said, neutrino-matter interaction can change electron fraction via positron capture. Basically, there are two reactions which can increase the electron fraction. One is positron capture, and the other is a neutrino capture. And please notice that positron capture, you need positron to switch on the proton capture. So positron can be produced only in a higher temperature regime. So we need higher temperature to proceed the positron capture. I'll skip here. And to see the importance of these weak interaction in the resulting electron fraction yields, we performed the full GL neutron radiation hydrodynamic simulation, including neutron heating. And I'll give you the result. These figures compare the contours of the temperature for SFHO and the Shen equation state in the orbital plane. As you can clearly see, the temperature for the SFHO is much higher than that of Shen, and much larger than 0.5, the rest mass of the positron. On the other hand, this reflects the fact that in this case, the mass ejection is driven by shock heating. On the other hand, for Shen EOS, temperature is basically less than 0.5, and we don't have any positron in this region. And
What is the proton-neutron story? Because if you look at this region, the center here is hotter.
Yes, high, yes.
So why do you say that the temperature here is lower than here?
Sorry.
Why do you say that the temperature on the right-hand side is lower than the temperature on the left-hand side? The center is much...
Sorry, okay. So in this region is bounded. So we need the other figure because for speaking about the unbound material, okay. And for this SFHO case, we have positron. And basically, because basically speaking, the ambient matter is neutron rich, this positron capture proceeds, and the electron fraction can be increased. And the anti-electron neutrino is emitted. In fact, if you plot the emissivity of the anti-electron neutrinos and compare the result with SFHO and the Shen case, you obtain the much higher emissivity in the case of the SFHO.
I have a question about the typical density of positrons and the typical local density of neutrinos. What is larger?
I don't know the exact number.
Well, you could do that same reaction.
Yes. So I can calculate, but current now I don't have such a number. So, but in principle, we can calculate.
Basically, do we have to wait for the positron number to get large, or can I just have a bunch of neutrinos that can do the same reaction?
Yes. So you mean which direction this?
If I have a neutrino on a neutron,
Yes.
I can get rid of neutrons that way too, right?
I think he's asking for the relative importance of positrons versus neutrinos and raising YE.
Yeah. But for this process goes left way, we need large proton fraction.
Well, I don't think he's talking about going the other way. I think he's saying both going to the right, but one case with positrons and one with electron neutrinos.
This one.
Yes. So I think he's asking
Basically,
top and bottom.
this process goes right way because of the large neutron fraction.
No, I think he's asking which is more important. In
Okay. So in the in the first 10 milliseconds, this reaction is important. After that, the temperature decreases because of the expansion of the ejector. The number density of the positron decreasing, and then this reaction becomes important in the later phase. And this is a resulting, sorry, this is almost black, contours of the electron fraction in ejector. For the FHAO case, as you can see, in the shocked region, the electron fraction increases to be larger than 0.3 or something like that. On the other hand, for Shen, the electron fraction remains low, in particular in the unbound material, less than 0.2.
So this is a equatorial plane.
Equator plane. And this is the a mass distribution histogram in terms of electron fraction for the electron fraction and the entropy per baryon. As you can see, for the SHO case, in contrast with the previous Shen case, the histogram showed spread broad and broad into higher Y range, like this. And the color shows the result in XY plane, and blue is for the X plane, and the green is for the YZ plane.
So I just have a related question. So if I were to turn off the neutrino radiation, which is the dominant effect producing this high Y material? Is it the hot positron captures, or is it the fact that you're doing the neutrino transport? Which is more important?
Now I'm performing simulation, and wait a moment.
What's that? You're running
Performing the simulation,
without.
turning off the neutron heating. So
Oh, okay, you'll be able to say.
just performing now. So
My guess is it's the neutrinos. I think the positrons happen once at the beginning.
Yes,
And then
yes.
you
That would be my
get
guess as
10
well.
neutrinos or something. You
Yeah.
capture 10 neutrinos to escape.
Yeah, that would be my guess as well.
and in each electron fraction, we perform the R-process nucleosynthesis calculation, and this is a representative result. And if you combine, or if you compile all of this result, we nicely obtain the solar abundance pattern. So this is a strong support for the binary neutron merger as the origin of our process.
How robust is that pattern?
Robustness is a very important question. So if you change the mass ratio, it seems that this result does not change much
For that equation of state, right?
for this equation of state. But the next question is this SFHO is only US for the production of solar abundance pattern? It's open. But in terms of mass, ejected mass, this equation of state is almost unique solution. Okay, there are a number of equation of state listed here, but for example, this black equation of state is relative mass density. If you use somewhat larger neutron radius, then you cannot obtain the ejected mass of 0.01 solar mass.
So do you have a plot of
Yes.
radius of the neutron star versus ejected mass?
Yes. Yes. So wait a moment. This is for the talk of next week. but I'll show you briefly. Here. Please remember these 5 equation state. SFHO is about 12 kilometers, and IUFSU is this blue curve. This is about 12.5 or something like that. But even such a very tiny change, the ejected mass significantly affected. This is ejected mass as a function of time. For SFHO, we can obtain order of 10 to minus 2. But slightly stiff equation state IUFSU, we cannot obtain such a number. So in terms of this ejected mass, SFHO is a unique, almost unique solution.
This is for a neutron star binary with mass ratio of 1. What's the
1 for the case of 1. But for this equation state, the main ejection mechanism is the thermal shock one. So difference in mass ratio is not so important.
I'm glad you have that strip there saying preliminary. This might
So
change for sure.
this is because this result is preliminary.
Yeah.
Why do you think 0.01 is the right number?
Sorry.
Why do you think this is the right number?
Okay, so why this number is right? Because if you have much less ejected mass, say 0.01 10 to minus 3, this means that you need unexpectedly high measure rate.
Too many events in my
Yes. 10 times frequent.
In order to
get all
In
that-
order
get
to
black
make
dark.
all of the R plus yeah.
But I don't understand how that matches with Brian, with what you were talking about at the beginning of the week, because you were saying that dynamically ejected stuff can easily be 10 to the minus 2.
Well, I was taking this from this series of
10 to minus 2 is also required by the kilonova event.
Well,
To explain the, yeah.
No, but from this list in the Hotokizaka, the compilation of these events, so with different equations of state, some of them were near 10 to the minus 2.
Yes, in that other time we don't implement the finite temperature one, but speaking about in terms of the radius of neutron star, the same level, and interestingly, this unique unique equation of state is preferred by the latest neutron star radius observation by Andrew Steiner, and also the chiral effective theory. And the constraint range is here.
I would object to that statement.
Yeah, the error is it can easily be the chiral
Yes.
effective theory can tell you.
Yeah, but
So to be clear, if you allow equations of state to go out of this region, you could get 10 to the minus 2 solar masses for other equations of state.
Yeah, APL equation, if you use a APL equation, that's right.
yeah.
So there's an upper limit on the radius that you can derive from this, right? Which would say that.
Yes, upper limit is between these blue and the yellow.
So the shock heating is a very strong function of radius.
Yes,
That's the main
yes,
point.
yes. I can show you.
But the tidal tails depend on the mass ratio.
Yes.
If you have big mass ratios, then you can have big tidal ejecta.
Right. So stiff equation of state gets a lot of tidal ejecta. Soft equation gets a lot of hot shocked ejecta. So conservation.
Sorry.